Alrighty, welcome to lesson 3 of unit 3. Today we're going to talk about a concept known as continuity. So by the end of the day you should be able to tell me what continuity is. Second of all, you should be able to tell me what the conditions are that make a function continuous or not. Some functions are continuous at a certain point and some are not. And you should be able to tell me what conditions do they have to meet in order to be considered to be continuous. You should also be able to tell me where a function is not continuous and where it is continuous. And then finally, you should be able to tell me for what reason it's discontinuous. Alright, and so let's go ahead and jump in here. Now the reason why continuity is so important is because a lot of the theorems that we use in calculus are predicated on the assumption that the function is continuous. So if you ever have a function that's not continuous, that automatically disqualifies that function from having certain theorems applied to it. So a lot of the rules that we use in calculus require them to be continuous. And that's why it's important to know whether or not a function is continuous, because if it's not, then you wouldn't be able to apply certain theorems to it. So let's start off with an informal definition of continuity. Now, before I read you this line, this sentence here, I've heard it put like this, and this is really the easiest way to understand continuous. If you start at a point and you go to another point, if you can draw a line from one point to the other point without having to pick up your pencil, then that's a continuous line. In other words, the line is unbroken. There's no holes, there's no jumps, gaps, or asymptotes, or anything like that. So this is an example of a continuous line. If you ever had a line, though, where on your way to the other point, let's say, on your way to the other point, all of a sudden there's a blank spot, that we would say is not continuous. We would say that that line has a hole in it. Okay? Or maybe on your way from one point to another, you're traveling along and then you jump to another spot, which we've seen earlier on other graphs. That's also considered to be a broken line. It's not continuous. Or one final case is if I'm trying to get from point A to point B, maybe I can't even get there because maybe there's something like a vertical asymptote in the way. And so as I try to get there, it causes my line to shoot up into infinity. And so they can never really meet. They never really meet each other. So those are 3 examples of discontinuities, okay? Because the line's broken. But a continuous line is one where if you can go from point A to point B without having to pick your pencil up once, then that would be continuous, okay? So what can we deduce from this? We could see that A, every point has to exist on the line. You can't have a missing point. B, the limit from the left has to be the same as the limit from the right, because if they're not, then you have a jump discontinuity, and that's a discontinuity, right? And also you're not allowed to have any infinite limits. Okay, the limit has to exist, the function has to be defined, and once you have those things, you're pretty much there, but we'll get a little bit more specific about it as we go. Okay, so here are the 3 scenarios. Here's a few ways that a function may be broken. The function itself may not be defined at C. In other words, there's just a missing point there. There's no point present. Or, in the middle, the limit may not exist because the limit from the left and right aren't the same. If we were to approach from the left, we would get a different y value than if we were to approach from the right, the particular x value there where the points are located. Now, here's a really interesting situation. Check this out. The function is defined everywhere. There's a point here. There's points everywhere along the line, except for right here, right? But that's okay because guess what? For that particular value of x, there is a point. It's just above the spot where it should be, right? So we can't say that the function doesn't exist, because it does. Okay? And we can't say that the limit doesn't exist either, because it also exists. The limit from the left and the limit from the right both meet at the same point. So the limit exists and the function exists, but here's the problem. The value of the function is not the same as the limit. So let's get a little bit more mathematical in how we define these then, okay? So in this case here, in order for a function, well, let me look at something really quick. So for a function to be continuous, here's what we need, okay? The function must be defined at C. So in other words, and this is something you'll need to write on your notes, f of C must exist. In other words, if you plug C into your function, you'll get an answer. All right? There's definitely a y value at that point. The second thing is the limit has to exist. The limit from the left and the limit from the right have to both be the same. So the limit from the left has to equal the limit from the right. And now there's a shorter way to write that, by the way. The shorter way to write that is like that. Because if the limit from the left and the right are the same, that just means the limit exists. Okay? So f of C needs to exist. The limit needs to exist. And then finally, on this example here, the function exists and the limit exists, but the problem is they're not the same. And so here's really the biggest point we have to make. In order for a function to be continuous, the function has to exist and the limit has to exist. And not only do they both have to exist, but they also have to be the same. If you can get that, then you know that the function is continuous. Now leave it to a mathematician to take something extremely simple and then make it overly complicated. So here's the simple idea. If you can get from point A to point B without having to pick up your pencil, it's continuous. That's the simple idea. But here's how it looks mathematically. Okay? Every point on that line has to exist. There can't be any holes. The limit has to exist for every point on that graph, meaning no matter what point you pick along that line, if you approach that point from the left or right, they both meet at the same spot. And finally, no matter what point you pick, the value of the function and the value of the limit at that point have to be the same also. If those three criteria are met, then you have this situation where you have a continuous line with no holes, gaps, or jumps. All right? Now that's a pretty popular thing on FRQ questions. It's not quite as popular as some questions, but if they are going to ask you any free response questions on the AP exam about limits, this is probably going to be the one they ask you. They're going to give you a function and they're going to ask you to prove that it's continuous at a certain point. So if you want to do that, you need to show that the function exists, the limit exists, and that they are in fact the same. And so buckle up. That's exactly what I'm going to expect you guys to do on your next test, because there's really not too many FRQ questions I can ask for limits. And I'm definitely going to be asking that one. So be ready. So here's a more formal definition now that we've discussed it. F of C is defined, the limit exists, and the value of the limit and the value of the function are the same. Okay? Now if you want to think about this graphically, if the function is defined everywhere, if you were looking at a graph, that would mean that you should not see any holes or vertical asymptotes. If the limit exists, that would mean you shouldn't see any jumps or vertical asymptotes. So as you guys can see, vertical asymptotes kill continuity. So if you don't see any holes, vertical asymptotes, or jumps on the graph, well then your graph is probably continuous. Your graph is probably continuous. All right, so this is a way of thinking about it using math symbols. This is a way of thinking about it using graphs. Okay, and we'll be looking at it from both perspectives. So, all right, so part A. Here's example 1. Part A is saying identify each point of discontinuity and describe why it is discontinuous. Describe each point of discontinuity and describe why it is discontinuous. All right. I'm going to start over here on the far left. I'm going to put a dot, and I'm just going to start tracing the blue line. And as soon as I reach a place where I have to pick up my pencil, we've got a discontinuity. And boop, there's my first discontinuity. I can't go past that open dot. So I have a discontinuity right there at x equals -3. Now I need to explain why that's a discontinuity. So remember, there's three things. Does f of that value exist? Does f of -3 exist? Does the limit as x approaches -3 exist? And then finally, are they the same? So we have to check three things. Does the function exist? Does the limit exist? And are they the same? Well, let's see. At x equals -3, is there a y value? Yes, there is. There's a y value at -3. The y value is 1. Let's see if the limit exists. The limit can be found by going from the left and also from the right. And if they meet at the same point, which they do, then the limit exists. And in this case, the limit exists because they meet at the same point. And the y value that they're getting closer and closer to is -1. So far we're good. The function exists. The limit exists. But are they the same? They are not the same. And so what we would say is the reason there's a discontinuity at x equals -3 is because f of -3 is not equal to the limit of this function as x approaches -3. So we have to identify the discontinuity. We also have to state the reason. There's really three reasons you could say. One reason is that the function doesn't exist. The other one is that the limit doesn't exist. And the last one is okay, well, if they both exist, maybe they just don't equal each other. All right, so there's one discontinuity. Let's start over now, and we'll see if we can find more. So once again, I'm just going to start over here just because I like to start from the beginning again. We're going, and boop, there's a discontinuity, but we already did that one. So now I'm going to skip it and keep going. We're going, and boop, oh, there's another one. I've got to pick up my pencil again when I get here. What's the x value of that point? I've got another discontinuity at x equals -1. Now let's see why it's discontinuous at that point. We have to check three things. We have to check to see if the function exists. So let's do that first. Does the function exist at that point? What is f of -1? F of -1, well, we do have a solid dot when x equals -1. It's right here. So the y value is 2 at that point. So f of -1 exists. Check. Nice. Let's see if the limit exists. What is the limit of my function as x approaches -1? Now, we have to do it from the left and the right. So from the left, the limit is approaching a y value of 1. And from the right, we're approaching a y value of 2. Oh, wait, sorry, back up. But since my limit from the left and the right are not the same, the limit does not exist. Wah, wah, wah. All right, so we're done. There's our answer. The reason there's a discontinuity there is because the limit does not exist. Now, just to be a little bit more specific about why the limit does not exist, we should say why, because there's three reasons, well, there's two reasons why a limit may not exist. One is because of this, when the limit from the left and the right are not the same. So the limit as I approach -1 from the left is not the same as the limit when I approach -1 from the right. So, now technically you might get away with just saying the limit does not exist, but I'm going to ask you guys to be more specific and explain why the limit does not exist. And in this case, it's because the limit from the left and right are not the same. Okay? The reason why I think it's important to be specific is because there's another reason why a limit may not exist. Sometimes limits don't exist because they are infinite limits. That's when you have vertical asymptotes. So I think we need to be more specific than just saying the limit does not exist. All right, let's do it again. So we're done with that one. So we found that the function is not continuous at x equals -3 because the value of the function does not match the value of the limit. We've also found that the function is not continuous at -1 because the limit doesn't exist at -1. And the reason for that is because the limit from the left and right don't match. Let's go ahead and see if we can find any more discontinuities. And we'll just pick up where we left off. So last we were working on it, we started here and boop, we went over here, we found that discontinuity. Now we're up here and we're going to keep going. So now let's keep going and boom, we run into another discontinuity. Well, you could tell right away this is pretty much going to be the same answer as the other one. Okay? So first of all, where's the discontinuity? It's at x equals what? 1. The x value of this point is 1. Now, as you can see, the value of the function exists at 1. We do have a y value there. F of 1 is -1. But the limit doesn't exist. Why does the limit not exist? Because as I approach 1 from the left and as I approach 1 from the right, I don't get the same y value. As I approach 1 from the left, I get a y value of 2, but as I approach 1 from the right, I approach a y value of 0. So my answer here is the same as this one. The limit doesn't exist because the limit from the left and right don't match. Okay? Let's go ahead and continue our journey. There's probably some more discontinuities on here. Let's keep looking. All right, so we started here. We found that discontinuity already. We found that discontinuity already. And we just discovered that discontinuity. And so now we're going to continue here. And I don't have to pick up my pencil at that point, so no discontinuities. I'm going to keep going. And woo. Now, I didn't have to pick up my pencil. And so technically we could say there's not a discontinuity, but the problem is the function never goes past that red line. I think what I'm going to do is I want you guys to do the same thing. Let's pretend that the function does go past that red line, and let's say that on this side there's a vertical line and it shoots this way. So let's just say the graph does continue after that red dotted line, and it's got an arrow pointing up, and then it slides over to the right after that. Okay? So let's say that, because I want to do one more thing. So, well, that's a discontinuity, because as I'm coming this way, I'm going down, well, I can never cross the red line. So if I ever want to get to the rest of my function over here, I would have to pick up my pencil and start afresh. And so I had to pick up my pencil. And that happens at the x value of at +4. So we have one final discontinuity at x equals 4. Now let's see why. F of 4. What is the value of the function at 4? Well, the function doesn't exist at 4. When you have a vertical asymptote, the function doesn't exist at that point. So that's why I had to pick up my pencil and move it. Now technically, you wouldn't be wrong if you said that the limit doesn't exist either, because we've also seen that for vertical asymptotes, the limit from the left and right, maybe they're both infinity or maybe they're both negatives. Even if they weren't opposites, it doesn't matter. If you have infinite limits, the limit does not exist. So technically, you could say this also, But you don't have to say both. You can really just say one. Oops. So, once again, you don't have to say both of these, but you could say either one, okay? When you have a vertical asymptote, that means the function doesn't exist and neither does the limit. So, right there, you've lost your continuity as well. All right, so we've seen a few different situations here, okay, and how to write our answers. And hopefully you guys wrote those down because you're going to be doing those too in a minute. But here we go. We had a discontinuity at -3 because even though the function existed and the limit existed, they weren't the same. They weren't equal. We saw that we had a discontinuity at x equals -1 because even though the function existed, the limit didn't exist because the left and right hand limits didn't match up. Same thing happened here, actually. Then finally, we had another situation where the limit on the left didn't exist, and actually neither did the function because we had a vertical asymptote. Okay, and so those are all discontinuities. Those are all places where I would have to pick up my pencil if I wanted to trace the line. And what's very important there is writing the reason, and I showed you guys how to write the reason for each one of those, okay? Now, before I do part B, I want you guys to practice this stuff a little bit. Okay? So, I'm going to tell you that our graph starts, it exists over here forever, so we have that. Put some arrows on here. Next, I'm going to tell you this, that we have a vertical asymptote right here. That's significant. And other than that, I'm going to let you guys see if you can find all the places where it's discontinuous. So I will tell you this much. There are 4 places where it's discontinuous. So the first thing I want you guys to do is I want you to see if you can find all 4 values of x where this function is discontinuous. So pause the video and see if you can find all the values of x where this function is discontinuous. All right, so the 4 places where it's discontinuous is at the vertical asymptote, and that's where x equals 0. That's the green dotted line I gave you. The next one is at this open dot here above the x equals 2, so that's another discontinuity. Another place where it's discontinuous is where it jumps from the solid dot here to this open dot, and that happens at x equals 4. And then finally we have another hole right here with a dot underneath of it, and that happens at x equals 6. So there's our 4 places where the function is discontinuous. Now we get into the really fun stuff. This is the stuff that FRQs are made of. Ready? You need to tell me why. Why is this function not continuous at x equals 0? So why would this function not be continuous at x equals 0? So pause the video and see if you can write the correct answer. All right, well, as I mentioned to you guys before, when you have a vertical asymptote, there's 2 different ways you could give your explanation for the discontinuity. One is you could say that the function doesn't exist at that point. But actually, you could also say that the limit doesn't exist either. And it doesn't really matter which one you say. You can say both if you want to, but you really only have to say one. All right, let's move on to number 2, the next one. Why is there a discontinuity at x equals 2? Now, I think your reason for this one is going to be a little bit more unique. I mean, I didn't have one like this on the last slide, but the way you write your answer will not be new. Okay, so see if you guys can come up with the right reason. And remember, your reasons are either the function doesn't exist, the limit doesn't exist, or the value of the function and the value of the limit are not the same. So you have 3 possibilities. It's going to be one of those 3. See if you can figure out, pause the video, why there's a discontinuity at 2. Well, when I look at this point here, do you guys see any y values? There's no y value anywhere here. So we have no, if I asked you what's f of 2, you would not be able to give me an answer. So the function does not exist. The limit does exist. So if you said that the reason is because the limit doesn't exist, you would be incorrect, because the limit does exist. The limit is that y value, which I don't know, I would estimate that to be about 0.5 maybe, but the function does not exist. There's no y value at that spot. All right, so now I want you guys to go ahead and see if you can come up with what's the reason why the function is discontinuous at the value x equals 4. Pause the video and see if you can get the correct answer. This one is a little bit more familiar, more like the stuff we did on the teacher example. Okay, we have a jump discontinuity. It goes from here and then it jumps up here. And when that happens, the problem is that the limit from the left and the limit from the right don't match up. We don't meet up at the same point. And when the limit from the left and right don't match up, well, that would indicate that the limit doesn't exist. So the limit as x approaches 4 does not exist. But I also said I want you guys to be more specific than that, right? So let's be a little bit more specific. Why does the limit not exist? It's because the limit as x approaches 4 from the left is not the same as the limit when x approaches 4 from the right. Okay? All right, last one, number 6. See if you can figure out why there's a discontinuity at x equals 6. Well, let's see. Does the limit exist? As I approach x equals 6, they seem to be converging at a common point there. I would say that that's a y value of about 6. So yeah, it seems like the limit exists. The limit seems to be about the value of 6. Yeah. So as x approaches 6, my limit is about 6. All right, fair enough. Does the function exist at that point? In other words, is there an answer for f of 6? Yeah, it's right there. When x equals 6, there is a y value, it's 4. But what's the problem here? They're not the same. The limit is 6, but the value of the function is 4. So we would say that the reason that there's a discontinuity is that x equals 6 is because f of 6 is not the same as the limit of f of x as x approaches 6. Okay? All right, so I'm going to go back to my teacher example now. This is just kind of like an inverted way of really doing almost the same thing. This one is asking me to identify the interval where the function is continuous. So we found where it was discontinuous, right? So back to our teacher example, we found that there was a discontinuity at -3, -1, 1, and 4. And then I cheated and added more graph over here. There we go. All right, so those are our discontinuities, but part B is asking me to find where is it continuous. Now, when you're talking about where a function is continuous, instead of just mentioning points, you're actually going to give intervals. So, for instance, from here to here is continuous. If I want to go from that closed dot to that open dot, you don't have to pick up your pencil at all, right? There's no discontinuities there. Now that's an interval though. It's going from x equals -4 to x equals -3. Okay? So now does the function exist at the -4? Well, since it's a solid dot, yes. So when the function exists, we're going to use a bracket. That means the -4 is part of that continuous interval. But at 3, since there's an open dot, that -3 is not part of the continuous interval, so we use a parenthesis instead. So there's one of our intervals. Now, you don't have to do this, but part of math is like, if you're going to put another interval next to it, we're going to put a little u there, and then we're going to start the next interval. So let's do that. So my next interval starts from this open dot, and it goes up to this open dot. And I didn't have to pick up my pencil at all on that interval, right? So we're going from x equals -3 for this one, and then we're stopping at x equals -1 for that one. Now both of those are open dots though, so both of those ones are going to be parentheses. Let's do another one. The next interval starts from here and ends here. I didn't have to pick up my pencil at all between those 2 points. And so that's another interval where the function is continuous. So I'm going to put another u, and now we're going to do that. So we're going from -1 to x equals +1. Now for the -1, do I use brackets or parentheses? Well, since that -1 there is a closed dot, we're going to use a bracket. The other one's an open dot though, so we'll put parentheses. And we just kind of keep doing that. So for the next one, we start here at 1. And I don't have to pick up my pencil until I get over here where I can't pass that vertical asymptote, and that's at 4. Now the 1 has an open dot, so I'm going to use a parenthesis. And the 4 is a vertical asymptote. Now vertical asymptotes you can't touch. So since I can't actually touch that, that's also a parenthesis. And we would be done here, but I added more, so put a U there. And the rest of it starts up here, right? And then it goes on forever after that. So how we write that? Well, it starts at 4, and after that it just kind of goes on forever. It doesn't. I put an arrow on there, so we can assume it just keeps going. And once again, you can't touch the vertical asymptote. And infinity you can't reach either. So infinities get parentheses as well. And so there you go. So it's just kind of like the inverse of question A. On question A, I was asking you where are the broken spots at. In part B, I'm asking you where are the non-broken parts at. And whenever you're talking about where the non-broken parts are, you have to use intervals. Okay? So that describes the places where the function is continuous. So now I'm going to let you guys do the same thing on the one you had. So for the one that you guys had, we saw that there were discontinuities at x equals 0, x equals 2, x equals 4, and x equals 6. So I'm going to ask you guys to pause the video here and see if you can write out all the intervals of continuity. And once again, I've color-coded my answers for you to check your work with. So you can just compare the orange interval to the orange part of the graph and kind of see how I wrote it. There's only one bracket in this whole thing, and it's at the 4, which is the brown piece that I mentioned there. Now, I erased these, but let's bring those back for a second. Yeah, I was going to try to color all of them, but it won't let me. Okay. Anyway, so these are my discontinuities. Now, I want you guys to notice that's where all the breakup points are, like right here. 0, that's my first one. 2s, there's my next one. 4s, there's my next one. And 6s, there's my next one. So that's the place where the pieces are joined together, right? Because those are the dividing points. That's where it goes from continuous to discontinuous. So that makes a lot of sense. Anyway, so there you go. That's continuity when you're looking at a graph. All right, I think we're going to stop there for today. I don't want this to go too much longer. We'll finish up this lesson on the next lesson. Anyway, so let's go ahead and, this is irrelevant. You guys can ignore that. That was something I had to do last year, but we don't need to do it this year. There is more to these notes, and we'll finish that up in the next lesson just because this one's just running a bit long, and I want to give you guys a chance to really digest the stuff that we've talked about already. And be able to do those. So go ahead and stop here, and then we'll resume it next week. All right, guys, see you then.